Good morning and welcome back to Chapter 1. Today we're going to be looking at Section 4, which is all about rates of change, tangent lines, and sensitivity. Not that kind of sensitivity, other kinds of sensitivity. First of all, our learning targets. We're going to find average rates of change of functions over intervals. We're going to solve applications involving rates of change and tangent lines. You're going to be able to find equations of tangent and normal lines. You might be thinking like, well, wait, I know what a normal line is. It's just a line. No, it actually has a definition. And find slopes of curves at indicated points, if possible. And find instantaneous rates of change. So that's what we're going to be looking at. Remarkably enough, a lot of these things are actually the same thing with different names. So it looks like a lot more than it really is. First of all, we're going to be looking at the average rate of change. Now, the average rate of change is what we've been finding before. It's just the the average rate of change from one point to another is f of b minus f of a over b minus a is the change of y over the change of x. This should seem kind of familiar because this is just the slope. The average rate of change is the slope. If we were looking at a function, let's say we're looking at f of x equals x squared plus 1. We could graph this. The graph of it looks like that. My left side is a little bit squished. And then if we wanted to find, say, the average rate of change from x equals 1 to 3, that would be, say, this point and this point. We're going to be finding the slope of that line. That line is called a secant line. A secant line, not the trig form of secant, although that's actually where that name comes from, but a secant line is a line that touches a curve in two places, or at least two places. So this is a secant line because it touches it in two places. If we wanted to find the average rate of change, let's say this was a ball that was thrown up in the air, so we have feet per second. A lot of times average rate of change is something over time. I mean, you could have the change of position over time. That's velocity. You could have the change of temperature over time. You could have the change of velocity over time. That's acceleration, a change in velocity. But a rate of change does not actually have to be over time. There was an AP question a few years back where we were looking at the rate of change of the temperature of a metal bar, like how fast the temperature is changing with regard to how far away from the handle you were. And so it was the change of temperature over meters. And so it doesn't have to be over time or with respect to time, but a lot of times it is. So if we wanted to find the average rate of change between these 2 points, we would plug in the points. We know f of 1 is going to be 1 squared plus 1, which is 2. F of 3 is going to be 3 squared, which is 9, plus 1, which is 10. So the average rate of change, that's average rate of change, is going to be 10 minus 2 over 3 minus 1, which is 8 over 2, which is 4. And then whatever units that we wanted to use. So that's what it is. And again, it could be like a velocity. We're talking about like meters per second. It could be the change of bacteria in a jar over days. So how many bacteria per days are there? And it could be anything. So I know a lot of times we think of rate of change as just a position in time, but it does not have to be just position in time. And so the next thing we're going to have is a tangent to the curve. Now, in our last slide, we saw, that was supposed to be a black line, whatever, with our deal, our squared function, we saw that secant line. Now, what we're going to do is we're going to move this point closer to the other point, because as we move it closer, it's becoming more and more of a tangent line. Now, a tangent line is a line that touches a graph in one spot. Now, that is a simple definition of a tangent line. That's not necessarily always accurate. It touches the graph in one spot in the area. And what I mean by that is if we had, say, a graph that looks like that, we could make a tangent line at this point. That tangent line is going to go like this. Yes, it does touch the graph again over here, so it is a secant line to the graph, but at this point, it is tangent. So I know that can sometimes be a little bit confusing because people think like, well, but it's touching it twice. It's like, yes, but at the point we're looking at, it's only touching it once right there. And it's not crossing through the line. It's not crossing through the graph. It's touching the graph, but staying on the same side. Like this tangent line would always be less than the graph in that area, as opposed to these guys up here where it crosses through. It goes from being less than the graph, less than the function, to more than the function. So that's why I say like tangent line, it can get a little bit tricky to define, but knowing what it is conceptually is a bit better. So how would we find this tangent line? Well, we're going to do the same thing we did. So we had our function f of x equals x squared plus 1. We're going to keep going with this function. And we're looking at the point x equals 1. So we're going to find a secant line that's just a little bit bigger than that. So we're going to go from x equals 1 to x equals 1 plus h, where h is just going to be a small number. And what we're going to do is we're going to end up taking the limit as h goes to 0, because that would put it right down to be nothing, essentially giving us the slope of the line at that point. So how are we going to do this? We're going to do it the same way. The first thing we need to do is we need to figure out what the y values are. So we know f of 1 is going to be 1 squared plus 1 is 2. And then f of 1 plus h is going to be 1 plus h squared plus 1. And we'll be working that out in just a second. And now we just find the slope. So our slope is still going to be f of 1 plus h minus f of 1. So we'll have 1 plus h squared, it's m, plus h squared plus 1 minus 2 over 1 plus h minus 1. What I want you to notice very first is in the denominator, those two go away, so it's just h. Being that this is always going to be basically what the x values are, it'll be something and something plus h. That denominator is always h, so we don't need to actually subtract. We can just plug h in, and when we see the formula, we will see that. So this is the slope, and then we're just going to take the limit as h goes to 0 of that slope. So now if we just plug it in, we're going to get 0 over 0. So what we have to do is we're going to take this up here. We're going to distribute out the squared. Limit is h goes to 0. So 1 plus h squared is not 1 squared plus h squared, right? I know I don't need to remind you of that because nobody wants to be that guy, but I just feel the need to point out that 1 plus h squared is not 1 squared plus h squared. It is in fact 1 plus 2h plus h squared. Then we have a plus 1 still. That would be that one. And then minus 2 over h. Now we can combine our like terms. What do we have for like terms? We have a 1 plus 1 minus 2. Oh, those cancel themselves out quite nicely. So m is going to be the limit as h goes to 0 of 2h plus h squared over h. So notice all the constants cancel themselves out. That will always happen, especially when you're working with polynomials. Because now what we have left, everything at the top has an h, we can factor an h out of that. That was a horrible limit sign. Limit is h goes to 0 of h times 2 plus h over h. We can cancel the h's, and now we can take the limit as h goes to 0. When we plug in 0 there, 2 plus 0 is just 2. So the slope of the tangent line at x equals 1 is 2. We can find the equation of the tangent line as well. We know the point. The point was 1 comma 2, right? We know that from just the equation. We're at the point x equals 1. We plug it in, we get 2. Our slope also happens to be 2. That is coincidental, but we can write the equation of the tangent line. Y minus 2 equals the slope times x minus 1. We can distribute 2x minus 2, add the 2, so y equals 2x. So if we make the tangent line, and what I do enjoy doing when I find this equations for tangent lines is I like graphing them, like with a calculator. Like graph y equals x squared plus 1 and graph y equals 2x and watch it as the graph comes up and makes a tangent line to your original function. It feels good to know that you got it right. So, but that's how we can find the tangent to a curve. We can find the slope of the tangent. We can find the slope of the tangent using this process. It's just the limit of the slope as the 2 points get really close together. And then we could use that to find the equation of the tangent line. So for the formula, slope of a curve at a point, we have the point a comma f of a, like we had 1 comma f of 1, which was 2. What you do is it's just the slope, y minus y over x minus x, which was h. The limit as h goes to 0. That's how you can find the slope of a curve at that given point. Technically, it's the slope of the tangent line to the curve at that point, but it's the slope of the curve at that point, which is kind of weird if you think about it. Like lines we've studied with slope because it's always the same, but like a quadratic, it doesn't have a constant slope. Its slope is changing. Its slope is increasing as we're getting more positive in this case. So if we found the slope at x equals 2, we would expect it to be a little bit higher because the graph is steeper at that point. The normal to a curve. So a normal line, what a normal line is it's a line that is perpendicular to the tangent line. Why is it called normal? It comes from the Latin normalis, and then it just kind of, which meant perpendicular, and then when it got Englishized, it just changed to normal. So if we have our function, that was supposed to be, that's not changing on me. If we have our function and we had that tangent line, which was right about there, the normal line is going to be perpendicular to it at that point. So it's the one coming straight out. And these do have a lot of applications. You have applications in optics, you have applications with vectors. They do have applications, and we will see some of those applications. But right now, we're just looking at finding it. And finding it is easy because the slope, like a perpendicular is, we know how to find the slope of a perpendicular line. If the slope of the tangent line that we found was 2, remember the slope of the normal line, so let's say this is tangent normal, the slope would be -1/2, right? The perpendicular line, it's the opposite reciprocal. So if we wanted to find the equation of this normal line, we'd have the point was 1, 2, so we'd have y minus 2 equals -1/2 times x minus 1, distribute 1/2 x plus 1/2, add the 2, y equals -1/2 x plus 2.5. And so if we extended this line and I drew it correctly, that's about where we would be. So that's how you find a normal line to a curve. Again, it's just a perpendicular line. So all that work we spent finding perpendicular lines in the past, it's going to help you. All right. So there's probably a little bit of a break right there. I accidentally pushed a button and it stopped my recording, so I have to do this slide separately. So I apologize for that little break and stuff. But the next thing we're looking at is the velocity and sensitivity. The velocity is the instantaneous rate of change, or what we're looking at with velocity is the instantaneous rate of change. That would be the velocity at a given point, at a given moment in time. And what that is it's the slope of the curve at that point. It's that limit as h goes to 0 of f of t plus h minus f of t over h. Now you might be thinking, it's like, well, how is this different than what we did? It's not, kind of. What we're going to see here is how to find it for any point. So back a few slides ago, we found the instantaneous velocity when x equaled 1. And that was great. We found it was going to be 2. So the slope of the tangent line at that point, the slope of the curve at x equals 1 was 2. The instantaneous velocity, if this was a position and time graph, at x equals 1 is 2. Well, what about when x equals 2? Well, we'd have to go through the same exact steps. What about when x equals 3? We'd have to go through the same exact steps. That can get a little bit irritating if you have to do it a lot. And to see like what the actual graph looks like is really great too. So what we're going to do is we're going to find the instantaneous velocity for any time t, or for any x value. And that's going to be changing because it's not the same slope the entire time. The slope's changing. So the instantaneous velocity is going to be changing, which means that when we find it, we're going to end up with an equation as opposed to a number. But then that'll help us. So if we remember back our equation we're looking at, f of x equals x squared plus 1. And we were finding it at x equals 1. First we started out from 1 to 3. And then it's like, all right, what about just 1? Now we're going to do it when x just equals x. Actually, I'll switch to t just because in the formula it's using t. So we're going to find it at x equals t. That way it looks like the formula, but you could switch out those t's for x's. It does not make a difference. So we have t and then we'll have t plus h for the second one. So we're going to plug in. It'll be f of t plus h, which will be the limit as h goes to 0. F of t plus h is going to be t plus h squared plus 1 minus f of t, which is t squared plus 1 over h. And we need to simplify. So we're going to have to distribute out this t plus h squared, which again is not t squared plus h squared. It's going to be t squared plus 2th plus h squared. Then we have a plus 1, distribute the negative, minus t squared minus 1 over h. Combine like terms, plus 1 minus 1 cancels themselves out. Oh, and look at that. T squared minus t squared cancels itself out. And what we're left with is, limit is h goes to 0 of 2th plus h squared over h. Everything has h's in it, just like before. Everything without h's ends up canceling out. Everything with h's is left. So we can factor out an h. So we have h times 2t plus h over h. Cancel. And now we can take the limit as h goes to 0. Hey, 2t plus h is it's going to be continuous, so we can just plug in 0, and we get that it equals 2t. So if we wanted to find the velocity at x equals 1, or t equals 1, we would just plug it in. 2 times 1 is 2. If we wanted it for 2, we'd plug it in. 2 times 2 was 4. If we wanted the instantaneous rate of change for 5, we'd plug it in. 2 times 5 is 10. And so this allows us to find it whenever we want. We don't have to go through all the steps every single time. And you might ask, well, why would you even do it the other way for just one number? It's a very good question. I always do it this way, and then I plug in the numbers I want, because very often you're going to need to do it for more than just one number. So that's the instantaneous rate of change. Sensitivity is just how much is something changing for a little change in the other variable, because variables work on each other. So for every little change in x, what is y doing? And it's the exact same thing as this. Like there's no difference. It's just another it's another way of saying the same thing, because instantaneous rate of change doesn't, like, the wording doesn't necessarily fit for every possible thing. So like, for example, the change of heat in a metal rod, the further you get from the handle. Rate of change doesn't make sense so much there, and so that would be the sensitivity. For a little change in distance away from the handle, this is how the heat change is going to be affected. So again, sensitivity, it's another word meaning essentially the same thing. So with that, I will see you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.